Okay, welcome back. I guess what we're gonna do in this video, next one, is continue with the basics of Cheat Engine. Right, I think we should start with this one. We can get quickly over how we're gonna use that tool, the basics from, I think we're gonna do 1 to 6 today, just to make it quick. But before we do that, I wanted to kind of update from the previous video some of the new things that we might use. Now, I'm not going to go over it right now for the sake of the time. But as we go, we're gonna have to use these tools a lot more often. And I forgot to quickly add this one. And basically, these are going to be everything you're going to be using for the most part. You're going to be using Detected Easy. Don't worry about it. As I've mentioned, I'll explain later on. GNSpy for assembly kind of editor. exe info, basically to kind of see what kind of architecture we're doing. Are we doing with 32-bit program 64 or any other information that we can get off the DLL or the exe? Kind of like a private injector for our DLLs from GitHub or from guided hacking. Ollie debug, which used to be the main source for this assembly. Now it's been kind of the successor of it is x64, and x64 can debug in both 32 and 64-bit, so don't worry about that. Reclass, similar kind of a debugger and looking to it. Cheat Engine, Assaultcube for testing, kind of like going there, getting our ropes and feet wet. But what I'm gonna do is I'm thinking of doing another game, and this time we're probably gonna do like a simple one, thinking of like maybe Ravenfield or any of those simple games. Kind of we choose to kind of have like two multifaceted sides when we're doing the cheats. But Assaultcube, we'll start with that, and then we're going into more different things. You need 32-bit in case you know that the game is using it. For example, Assaultcube is 32-bit, if I'm not mistaken. Let's see if we can keep quickly. Detected Easy. Let's see if we can quickly figure that out. Right. Unknown. Batch file. 1 second. Where does it keep its client? 32-bit, yeah. So it is a 32-bit kind of game. So we can just use 32-bit cheat engines, just to save a little bit on time and memory. Hex editor, professional, IDA professional, basically very advanced disassembler, and of course our two code editors. You can use Visual Studio Code, but Visual Studio 2022 might be more convenient for some people. Anyways, let's actually get into the main video. So when you start this, the one you're going to be using is going to be the 32-bit one, or the one that without, if we can quickly open it. This is the one without, it's just the regular one inside the cheat engine. And if I'm not mistaken, it just uses the 32-bit, it's x86, I think. See, this is where our tools come in handy. And we can actually figure that out, what our tools we might even use, right? So let's see. Cheat engine, 32-bit, yeah. So when you launch it, if I'm not mistaken, I hope this is not a container GUI. Yeah, so I think it uses a 32-bit. So if you want specifically cheat engine that works for a game that uses 64-bit, and you go for that one. But anyways, I digress. This is essentially a good tool to see which tool you even need to use, right? But going back into Cheat Engine, when you launch it, at least when you type in Cheat Engine in your search bar, it's going to give you this 32-bit, or at least the architecture is. And for the sake of it, we're going to be using the tutorial for the x86. So x86, think of it like 32-bit. It's based on the architecture naming scheme back in the day, and back then they called it x86. And basically what it means is there's just less memory that registers can store. It can only store 32-bit. So I think that's 2 to the power 32. Can be one kind of data register. And x64 means that like one section can be 2 to the power 64, so it can hold a lot more data, a lot more, like a bigger digit inside its register, which is a lot handful when you're having to do with transferring files, when you have the data storage, all that. Anyways, I think we're going a little bit off topic. So the whole point is this kind of gives you a basic rundown of how Cheat Engine works. And essentially when you open it up, it's going to tell you, hey, this is the password if you want to like skip to a specific section. Honestly, if you feel like you can't do it, there's a skip button. I'm pretty sure that is here. Yeah, there's a skip button. But for example, you enter this number and you can go to the specific tutorial for your cheat engine. I don't know if this number actually changes. I didn't check. But let's do the basics of what are we trying to do in game hacking. We're trying to look for values inside your game, either that you can see or you can't see, that you know if you don't know if, and we're trying to get where that value is in memory, right? So what can we do? How do we do that, right? So first of all, we need a tool that searches it, and Cheat Engine is the perfect example for it. So what we're going to do is we're going to attach Cheat Engine, right? So Cheat Engine basically starts monitoring memory coming in and out, and what's the memory and what addresses the memories are, and what these addresses values that they hold, what kind of values they hold, what kind of data it holds, is it an integer, if it's a double, float, like basically the whole shebang. So we're going to attach it specifically, right? You can do it by application, right? You can do Cheat Tutorial, right? Because it's its own standalone, like a thread, like its own module application. You can do by process, which I think, yeah, Tutorial has its own direct process, because to do that it needs its own kind of ID or its own handle for the window. Or you can do it directly by the windows, right? And sometimes, even though it's like a multi-thread, sometimes you can select a window, but it'll be on the same process because there's no multi-threading. It's like basically the program is running as like a one module function. When you start going into threading, which means using multiple CPUs, multiple paths at the same time, basically that's when you start to see kind of this split of multiple windows for multiple kind of like processes for the same kind of program in a way. But they all kind of do share one main kind of address, or I guess I would say like house, right? House number, right? But that's a little beyond that. Anyways, so we're gonna attach it to the tutorial, right? So now Cheat Engine is monitoring for all the values within it. And in this tutorial, right, or at least for step 2, they asking us to have a health value of 100, right? And they want to find what is the address of this health value, right? They want to figure out what this health is, where it's stored, right? What's the address, what's the house, and then change it to 1,000, right? So this has to basically, you have to hack it so that set your health to 1,000. Okay, so first things first, I don't think did they explain? No, I don't think. Yeah, they don't really explain necessarily how it works. But to kind of make it simple, 4 bytes for most games, right? When you compile a game, we saw 32-bit, right? When the compiler does 32-bit compilation, where it tries to save space, any data type that is an integer is just a data type when you code, stores 4 bytes of memory. What is 1 byte of memory? 1 byte of memory is, I don't know if we talked about this. I think we did. Let's say 11. So this would be 1 byte of memory, 60, right? Sometimes it can also be FF, right? So you can do, right, this will be 1 byte of memory, 1 hexabyte of memory. And essentially 4 bytes just means, right, this, right? And you can even see this is the maximum an integer can be. And I believe this is specifically for 32-bit. Realistically, actually can't be this much. It actually is divided by 2. but we will go into, when we start coding, I'll explain better the data types. But basically think of it, when games have a simple number that they need to track, that is an integer, it can't be a decimal point or anything, it's just a simple number. A lot of times they'll use an integer just to save space. You can save space even more, but for the most part, they will use 4 bytes. Maybe older games like Doom might use bytes or even binary, but modern games use a 32-bit and they kind of default to an integer that is 4 bytes. So most things that you search in a game will be an integer of the size 4 bytes, or at least simple values, simple games. So let's search for 100. Right, we do a first scan, exact value, 4 bytes, and we scan for it. We found 58 addresses, right? But we don't know which one it is. Well, how do we figure it out? Well, we need to change this value again. Well, we actually know that this is not probably the value because it changed and we didn't even do anything. So most likely these are not the value. You can manually delete them, I think, if you press remove selected addresses. Yeah, you can do it like that. Or you can just do the next scan and it will automatically filter them out. So now we have 98 after we press hit me. You can actually maybe even see it. It's right here, right? But in reality, you'll have thousands of results. This is just a very simple example. But realistically, you will need to do the scan multiple times to get the value that you want. So now we got 98. Now what do they want us to do? 1000, right? And hit me. Yeah, okay. That's great. Next one. So this one is a little bit tricky. What if we don't know our health value? Well, let's say our health value, it's like let's say our health value is like it's like a health bar, right? Like a right, or yeah, like a health bar, right? Like it's like in Dishonored, right? I think I'm pretty sure it's a health bar, I think, or even honestly, you know, in Call of Duty, when your health is, it's not even shown on screen. It's like you see the screen, and if your health gets low, you see kind of like blood splatters start like creeping into you, and the game starts going like gray. So in a way, that is a hidden health value. And that is basically, they're actually asking you, give an example how you'd find it. Now we know it's between 100 and 500. I would not, when you do this tutorial, don't assume this, right? The whole point of this tutorial is to kind of give you like, hey, what if you don't know at all, right? You don't know if it's between 100 and 500. This is just more like a hint for you to keep going. But let's say we don't know what it is, right? So we set it to unknown initial value. We assume it's a 4 byte. If we can't get it, we keep trying other values, of course. But assuming it's a different value, let me actually delete it. We do a first scan. We found a total of 533,000. Now that's a lot of values. Let's try to lower it. How else we can lower it? We can say unchanged value, because I didn't press hit me yet, right? I just, let's say I'm in the game, right? I can just run around, do something, open some windows, like move around the window, set different things, go into the pause menu and press next, and it will probably filter out a little bit. Now a lot of times it actually doesn't do a lot, but it's still better than nothing. It's a good little start to go with. But the best way is to make sure that the value we're looking for actually changes and know where we changed it to. So let's say if we do hit me, we know that the value is going to be decreasing, right? So click hit me. Now we know that all these values that are 0, clearly not the values we're looking for. So we have to look for a value that decreased. Oh, look, now we're at 1600, a lot less. You can even, if you're really adamant and you have patience, you can find your value just by trial and error. There's a good chance you might actually crash the program if you try to change things. So the best way of doing it is to get as little of this number possible, and then when you for sure can't figure out if you have a little bit of a problem, then you go the manual method and go one by one, or use any other strategy. But try to get this at least to, I don't know, I would say my go-to rule is if I can't get anything below 100, I probably should restart and try again. If I do have 100 or below 100, then you can kind of play around and see which ones you can manually remove and so on. But in this case, right, I'm actually gonna do this, right, lower it more, and I'm gonna hit it again. And I'm gonna do decreased value. So we know that it's these, one of these 4 values is probably our health address. Now I know it's 288. This, I think, if I'm not mistaken, and I didn't really look into this, but it's an address to something else. If I'm not mistaken, it might be a pointer or might be a display address that is kind of like displayed differently, because it follows the same pattern and decrease as this 288 value, right? It decreases the same amount. So there's a good chance this is like a storage value for something else, possibly for display. Not exactly 100% sure. I'm not too keen on figuring out, but if you're ever interested, you can go for it. Now they ask us to change it to 5,000. Now we hit next. Okay, step 4. This one I will go a lot faster. Same idea as 4 bytes, but instead we're trying to search for decimal points. Both of these, right? Okay, so let's search for 100. This might be a problem. So let me actually hit them first. Be a little bit easier. This is going to be kind of your real scenario. Now the rounding basically means that, let's say you have a 95.5999, it will round to 6, right? It will try to round to a specific truncated kind of number. I honestly forgot which exactly it does. What's the number? But I think this one is rounds by, like, let's say if you have 5.58, I think it might even round to it. While default is a little bit lower, right? It's just like based on a specific number, like a small variable that it does. But anyways, let's do first scan. Actually, let's delete these results. See, right now it kind of rounded the 5.999 to this number. And we do this. And then we do another scan, but this one is a double, right? So this is double is basically the same thing as float, but it has double the precision. So, right, you can have a decimal point to, I forgot the full, but let's say you have the decimal point to do, like, let's say 0.0001, right? Well, this is double of that. It'll be 0.000000001, right? Like, I forgot exactly how it goes. I don't want to get into it yet. When we start coding and doing the C++, I'll better explain like the doubles and the difference between the floats and whatnot. Then 90, let's do the next one. Oh, 99, sorry, 0.5, first scan. And then we'll do this one again. Oops. And then we go next. Okay, now we'll do in a code finder. So basically, this kind of wets your feet of how would you look at like a code, like a disassembler, right? And basically, what it's trying to teach you is, let's say you have a memory instruction. How would you nullify this instruction, right? So basically, give you a very, very simple example of how would you modify an assembly instruction to do what you want to do on the most basic level. And the most basic level is, if there's an instruction that it hits, instead of doing the instruction, don't do it, like skip it, right? So it kind of quickly teaches you that. So first things first, we will find this value. First scan. Oh, new scan. 4 bytes. First scan, change value. We'll go to 300. Next scan. And this is our value, right? So we have a value and we have the address in memory where this value is. Now what we can do is find what writes to this address, right? It will attach a debugger so that you can see the instructions in assembly, kind of memory form. When you click the change value, you see this is the instruction. Now what this is if I'm not mistaken, these are operational codes. Move, right? I don't know if we can. Right, move, call, jump, add, right? Like these are all register instruction codes for your registers, basically in your CPU architecture, to do simple instructions. So basically, add two numbers, subtract two numbers, move this data into this data or in this register, jump. Basically, jump is used a lot for loops, right? This is how you represent code in assembly, right? With these opcodes. And once you get better, you'll start to easily see what these instructions are doing, right? So what this means is that it's taking whatever the value in EDX and we're putting it into REX. You can even see that right here, right? What we're gonna do is we can even set a breakpoint, right? And to see, will it hit the breakpoint when we do change the value? If it does hit the breakpoint, then we know that this is the correct instruction that is being executed. Oh, guess what? It hit the breakpoint, right? And here we can see 2CF and the address right here. So what it's doing, so here's a little trick that some people might get confused. The RDX and the EDX. In a 64-bit system, the register, right, the full portion of the register, the 64 portion, is RDX. Now, if you're not going to be using the full portion and you're just going to be only using the lower portion, like let's say the 32-bit, so half of this, right, you don't need to use all these numbers to represent the moving and everything. You only need to represent the last half, and the last half means just the bottom. And in terms of like from left and right, it just means everything on the right side, right? It's from 0000 to the right side of it. You can even actually see, right, what the instruction is going to do, because what we did is we breakpointed before it's about to happen. We didn't step into it. So we're about to execute this. So what we're about to execute is we're going to move RDX. It says EDX, so like the lower portion of RDX, and we're going to move it into REX, which is here, right? So to explain a little bit better how you can easily understand this, let's to CF, right? 2CF. So after, what's going to happen is in REX, right, which is the, you can even actually see, which is the address, right? So REX holds the address. We're going to move the value of the RDX into the value. So we're going to move the, we're going to move the RDX into the value of the REX. So this points to an address, and that address will now have the value of RDX. Or yeah, RDX or EDX, right, in this case. And that value is going to be 719. So watch, this number is going to switch to 719, which is the representation of it is 2CF in hexadecimal. Step into 719, right? Now it's 719. The value is 719. All right. I hope you're understanding a little bit. This is kind of the basics of how memory is moved and how your game works. It's just a bunch of memory going back and forth from register to register with instructions using the assembly language. And that assembly language is essentially how it's like dictated is by the code somebody wrote in C++ or C, right? That is, might sound confusing to most, but that is the basics of how it works. Now, what we're going to do is we'll replace this code that does nothing. And what do they infuse edges with a high enough speed in it? Yeah, it does say it right here. Replace optional, replace the code that does nothing. Okay. Replace the code that does nothing. And this just means, hey, name your code. You can see all these snippets in advanced options, right? And what we did is we nopped it, right? So the instruction right here that is supposed to take MovieX, this will now not be executed, right? When we change it, nothing happens. Oh, remove breakpoint. Run. Yeah, sorry, I forgot that we breakpointed the instruction itself. Now we can go next. And we can delete this. Okay. So this is pointer basics of pointer finding. All right, so before I start explaining, let's start first find the number that we're looking for, 339. And now we have our value. Now this is the address to our value. Now, the way sometimes a game works is that, think of it when you start a game, there is the top house number, right? Like the address of it, the base address, the static address, that then dictates what's next going to be. Because every time you start a program, let's say you restart or give it to another person, whatever that build of the program is on your system will have different addresses every time you start. So these addresses won't be the same every time you start your program. In rare cases, it could be, but for the most part, programmers for games are not thinking of kind of maintaining a specific addresses or somehow making it adapt to this. They're just gonna have Windows decide what that memory is. It's gonna give them that perfect specific module, which will be the static, and then they will offset and create addresses based on what memory they get. Now, the one that we got this time is this number, but we're not actually, like, this is not actually the correct number, right? So this is not the correct address, like not the base address where this value comes from. So in order for us, for example, to, like, let's say use this once we restart the game, we need to actually find the base address. Then with the base address, we know when we go back and basically do the pointer arithmetic, we can figure out, hey, oh, we found all these offsets just to get to the pointer. We can create our own little address manually to constantly point to the value. And by entering the offsets that we figured out on the way, on the process backwards. Now, how are you gonna do that? Well, we know that this is most likely a pointer, right? You can figure out if this is a pointer by just searching this number twice after, removing your game and launching it, and then you search it again and you realize, oh, these addresses 10. So most likely this is not the correct pointer to it. And just a little tip that none of these addresses are going to be a flat address the first time you search this. You always going to need to figure out that this is probably a pointer. You just need to figure out how many levels up it is up to your main static address or main base address. So how would you do that? So the basics of it, the most basic way of doing it, let's say you found this, you search for this value. Now we know this is, the addresses are usually represented in hex. So you search for actual hex value. And we found it. Now to explain this, what we did is we found a pointer. What a pointer is just a value or a box of memory that holds not a value of something that it needs to hold, but an address. And that address then this points to another address and so on. So the idea is a pointer is just a variable that holds not something that we need like a data, but just holds the address to another variable, kind of points to it. The reason why we do this is in C++ and C, a good method of coding is actually pointers, and pointers basically can direct you to other sections of your code and functions back and forth instead of manually coding them line by line or referencing them. It's a very handy tool, and it makes you write a lot less lines of code, and it makes a lot of interesting things. It's a very powerful tool in terms of coding on C++. We'll get into that when we get into C and C++. But now we figured out our pointer. Okay, so we know, you can kind of tell this is a base address for the most part. It's because you can already see the tutorial x86, right? So the base module. Sometimes it won't say something like this. It'll be like a base, a different kind of way. But a good handy way to even tell is that even Cheat Engine will tell you, hey, it's green. So it basically means that this is like the static base address itself. So now we know that it's this address. Here's what we can do, right? We can do add the address manually, make it a pointer address, right? And basically, the reason why we put 0 here is because it's just one offset, right? Like it's one pointer offset. Once we have multi-level pointers, we keep adding them more and more and more, and then it will be a little different offsets, off the offsets and off the offsets. So kind of it would be like multi-layered of pointings to the actual value. For now, this is simple. It's just one level, so we don't have to worry about it. So now we made it a pointer that points to our value. And let's say we change the value 39, right? It's still gonna show this one. But let's say we change the pointer. If we change the pointer, that means the address of it, I think, yeah, the address of it in this case goes different. It will point, so the address, yeah, so the address of the pointer will stay the same, but I think, but the value of it will change to another address. And now this address will be pointed to something else. Our health value will be different. So here's an example, right? Clicked it, right? Our health now is 168. This is the correct health, but our old address basically kind of got cut off. It still keeps the 396, but it no longer is what the value that we need. So this address is useless to us. And yeah, so it actually didn't change anything. What it did is basically cut off that entire memory, restarted and created a pointer again, and it created to a different kind of section of memory. And this is now the new address that we're supposed to use. If you still had the old address, you would have basically lost the address, lost what value you have, and you have to redo everything again. With a pointer, and the fact that we added our address manually, now anytime this pointer changes, we can still access where it leads to, what health value, right? Just value, I guess, what value it holds. Very good tool. Now it asks us to change to what, 500, if I'm not mistaken. And then freeze it, which basically means just activate and freeze it. Let's say I change it. Right, and next. Okay. I think, yeah. So for this one, we will go into the next part of the video. For now, what we did should be sufficient. So what you learn is basically basics of searching for values of integers, of floats, and doubles. You searched we learned a little bit of how instructions work and how you can basically nop it, which basically means to kind of nullify it and make the code run nothing when it does hit it, how to breakpoint into it, how to attach your own debugger into find out what writes to this address. And we kind of went over some of the old new tools that we've been using. In the next video, we will go over a little bit more advanced steps of the cheat engine. So thank you guys for watching, and I'll see you guys in the next video. Bye bye.